Hi everybody, welcome back to Multimedia Programming. Today about machine learning part 2, a neural network as a function approximator and regression. So as usual, you can find the links for this lecture on our on the links in the description below and also in Moodle. So today I will show our Colab notebook for the lecture because that includes the software, the programs that we want to try. So first let me start with this little picture here that was generated by DALL-E, basically visualizing a neural network as function approximator and regression. So I thought it was kind of nice. So let's start with a definition of our problem. So here you can also find further videos. So we can use a neural network as a function approximator, which is defined here. So we have a y, and this is the function value, and then we have a function f of x, and x here in our example is a one-dimensional input, for instance time. So if you want to have a time-dependent function, for instance generating some audio signal, then x would be time and y would be the audio signal or the sample given the time index. So it could be, for instance, a signal like a tone, or could be a sinusoidal function. So the x would be the time dimension and y would be a sample from or to the sound card. So in PyTorch we have torch sign function, which directly produces a torch sensor, and also torch randn function, which produces random numbers according to a Gaussian distribution with zero mean and unit variance. And we can use this to simulate a microphone and pick up noise. So that's quite practical. So we generate our target function with the code below. So this code also contains the preamble here. And here you can see we import the necessary libraries, the Torch library, Torch neural network library, and matplotlib pyplot. And we can also choose if you want to run it on a CPU or CUDA. So that depends on your on your hardware. So in my case, or in our case, we use Colab here. So depends on what Colab you have. You can either use CPU or CUDA if you have a GPU. So then we can define the number of samples in our signal here. In this case, 40 input samples for our signal. Then we define our time axis, x. So this is basically the time string. Goes from 0 to n in steps of 1. So this generates the n time steps. Then we add the last dimension for the signal. So we have one sample each. And the first dimension is for the batch of size n. So basically this is what PyTorch expects. It also expects this batch dimension. And then the y would be our target. So here we have our sine function. So it takes our x, our time input, and here multiplies with pi divided by n times 2. So if x goes from 0 to 1, then this would be 2 periods for n samples. And then we also add random noise to it. So this is normal distributed noise scaled with this factor of 0.1. And then we have our 2 periods. And we can here we can check with the printouts if the dimensions are correct. And yes, both dimensions are correct. So first dimension 40, so the batch dimension, and then second dimension is just 1. So often we want our network to interpolate the function. So here we have integer samples. So often we want to interpolate between those integer samples, which are the training samples here, and also to extrapolate beyond the training samples, so go beyond those 2 periods which we define in our training. So hence we construct a validation set which has the x samples between the integer values of the training set and extend it to beyond the length of the training set. To see how robust our network is against the noise in the training set, we also add new noise. So this is now our validation set. So here we have our x in the validation set. So this starts at 0.5, so in between the integer values. Has twice the length, so 2 times n. And has integer steps. So it starts at 0.5 and the next one is 1.5 and so on. So it's basically just shifted by 0.5 compared to the training set and longer. Again, we add the batch dimension here and construct the validation target function. So here we apply the sine function to this longer shifted input. And that's it. So now we have to decide what kind of network to use for our approximation. So we try to find one which is as simple as possible for the task. So we choose a structure which is in principle able to approximate the function piecewise. So we use a number of nodes in the network, and each node is in effect responsible for a piece of the function. We do this with a 3-layer fully connected network with activation function, which you can also see described here in this link from Stanford University. So the first layer of our network is the input layer, which takes, in our case, one input sample of x, so here the time, then distributes this sample to n hidden nodes. So here are our n hidden nodes. They also have a bias, which basically activates each hidden node for a certain value range of x. Right, so you can think of each node here in the hidden layer having a different bias, and then the output has an activation function, which is a nonlinearity. So you can think of the bias shifts it in the active region of our activation function, and that means we can approximate different pieces of the function with different nodes. And the activation function, for instance, can be the sigmoid function, which is mainly active in the range of roughly -4 to 4. And then this is followed by weights of the output layer here, which in our case is simply one node which sums up all the inputs from the hidden nodes with weights, but with no activation function in our case. So in general, this could also be having an activation function. So altogether, this can be seen here in this picture. So fairly simple. You have some input here. Then this input goes to the different nodes in the hidden layer. Each node becomes active at different levels of x and produces the corresponding output of the function. And then all of them are added together to produce our function approximation. So in Python, we can implement it like in this code. So here we chose 10 nodes. So basically you can think of our function as approximated by 10 pieces. We can also change it as an experiment. So 80 can result in overfitting. So that means it models the noise instead of just the function. And here's the actual definition. We have a class which we call LinNet, linear network, which contains of 2 main parts. First, the initialization, and then in the forward function. In the initialization, we define the function and the initial setup. So here we can see we have the definition of layer 1. So here we have a linear layer which has one input feature and nodes output features. So this basically represents our hidden layer. So you can think of the input layer is already part of it. And then this is our output layer. So this has in features equal nodes as input, so from the previous layer, and out features is 1. So that's our function value. And both have a bias. Then we also define our activation function as the sigmoid here. So in the second part here, the forward, we actually put those functions together. So first we take our signal x, the input, feed it into layer 1, produce an output. Then we take this output, apply the activation function, our sigmoid function. And finally, we take this output and feed it into the output layer to produce a single output value here. Yeah, so then we, after we have it, we can now do the processing. So in the following main section, we instantiate and initialize the model, which is initialized with random weight values. And part of the printouts are the initial weights before the optimization. So there you can see the shape and also the random initialization of them. So that can also be interesting. Yeah, so here you can see it. So we can also then observe the loss values during training and see how they hopefully decrease. So here we start with instantiating our linear network model, the 2 device. Then we try to predict something before training. So here this would be the starting value of our network. Here we can also read out the weights of our network before training and print them. So here we can see the shapes and the random numbers. Here we need to define the loss function. So we take the mean squared error loss for our function approximator, which sort of makes sense. And here we define the optimizer as ADAM. And ADAM works on the model parameters. Then here is the optimization loop. So you can see this is a for loop going over 10,000 epochs. And you can see here it starts by checking the output of our model. Then it computes the loss function, comparing it to the target. Here we can, every 100,000th epoch, we can see the state of the optimization with the epoch number and the loss. And here now is the gradient descent steps. So here the previous gradients are set to 0. Then here back propagation of the gradients, and then here the update of the weights to hopefully make the loss smaller. Yeah, and then we can let it run and see how fast it is. So we can just click on those 2 cells. So here's the definition. I guess there's another one above. Yeah, so actually we need to run all of them. So first this one here. So this is just the setup. So first Colab needs to connect, and then it should be fairly quick running the cell. Yeah, so here now we have the results. Then here we have the validation set. Here we define our neural network. And here we now do the optimization. Yeah, so here you can see the initial weights, their shapes, and it's basically random numbers. And here's the optimization. And you can see here we start with a relatively high number of 0.79. And in the end, we get down to 0.01. So indeed, this number became smaller and smaller. And then we just stopped at 10,000. Yeah. So now we can compute the resulting loss value of the training set and also the validation set and plot the obtained learn function in comparison to the noisy target function for training and validation. So for plotting and printing, we need NumPy arrays. Hence, we need to convert from PyTorch tensors to NumPy arrays before we do that, which we do with the function detach NumPy. So detach basically removes the gradient part information, and NumPy turns it into a NumPy array. So here you can see it. Now we have this trained model. So now we put in our x, and we get the predicted values from the trained model. So this should be good. Now we can also compute the resulting loss function. Hopefully it should be small. Then we try the same with the validation part. So this is maybe more interesting because this was not part of our training. Again, we compute the loss function. So let's run it. Yeah, so here you can see the loss on the training set. So we have this 0.0114. Here we have this 0.0114. Actually, this is not the final value because it runs until 10,000, but 10,000 is, or one before 10,000, but that's not printed. So here's the loss on the validation set, 0.009. So you can see here, this is actually a little bit lower, kind of surprising. Yeah, so that's a good sign. Yeah, also when you look at the printout of our initial weights, we can see the dictionary entry for layer 1.0 weight. Right, and this is a two-dimensional tensor or matrix which represents the matrix A of the first layer of our network. So here we see this formulation. So this is how our linear network is defined. We have some input x. In our case, x is just one sample. Then we have our matrix T, A, and in our case, this is the hidden nodes output. So we have n hidden nodes, 10 hidden nodes, and that means we have 10 output values. So that means A is a vector of 10 values, or a 1 by 10 matrix of 10 values. And then we have a single value here. No, we have 10 biases, so we will also have 10 bias values here in our initialization. So let's check. Going back here. So here, layer 1.0 weight. We have this tensor here, and we indeed get 10 values. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we can also see this layer 1 bias, which is added to each node. And here we can see we also have 10 values. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that works. Yeah, so this is basically the mathematical function which is implemented using this network and then followed by our sigmoid function. Yeah, then we have layer 2 weights, which are the weights for the next layer, which is the n, which has n input features and 1 output feature. Basically, this produces our function approximation. Hence, it has 1 row with n elements. And finally, we have the bias for this layer, which is only 1 entry, since it only contains 1 node. Yeah, so after the optimization runs, we obtain the losses. Usually the loss on the validation set is somewhat higher, unlike what we just had, than for the training. but less than a factor of 2 usually, which is not too bad. So this is important to check because we don't really know, since it was not part of the training set. Also, since we have this random starting point, the result might differ each time that we run the optimization. And that also shows that it's important to check every time, and also to check if the loss values are low enough for our application. So if not, it could happen that that the optimization is getting stuck in a local optimum or local minimum, and then it's worthwhile to restart with a different random initialization starting point. So often it makes sense to try different runs and then see which works best. So maybe we can also try it here. So here we have 0.011, and maybe we can run it again and see what we get. So we have now different initialization values. And you can see we start also at a higher loss function. And here now we have 0.04, so it's actually much higher. So here you can now see we have 0.04. Here validation is 0.0418. So this is now slightly higher than on the training set. So it shows it depends a lot on the starting point. So maybe we can start again. Here now we have an even higher starting point. So we were lucky the first time around. But here now it actually found a good minimum anyway. Right, so 0.011 seems to be fine. So let's try this again. And here we have 0.011 and here we have 0.0099. So again, it's actually slightly lower. So that's nice. Yeah, so let's check. Here we can now plot the results. Here, this plotting cell. So it plots X and Y, and yeah, here the training target and the prediction output. So Y is the target, Y pred is the predicted output, and you can see here blue is the noisy target. Remember, we added noise to it. And now the orange line, the orange plot, is the predicted output. And since we only have 10 nodes, it has the smoothing effect, right? It doesn't really, it cannot model those fine details of the added noise, and that's why we have the smoothing effect. And that has the effect of denoising the sinusoid. So this could be used for denoising a function. Yeah, and also that shows if we choose this number of nodes too high, then it will be able to model the fine details of noise, and we will have approximated this noisy function more closely, but maybe that's not what we want, right? Because if noise is random, then we don't want to model the noise because it's different each time, right? It's not something that is part of our signal, but is something we don't want to model because that makes generalization difficult. Yeah. So we see that we indeed get a smooth version of the training set, which means our network is somewhat robust against the noise on the training set. So now we can plot the validation set, which is always interesting because it's always doing something different. So here from some previous run, let's see how we did today. Yeah, so indeed it looks different. So here the first period here basically is our training set, and then after it, basically the network imagines how it could continue, right? And this is what our network is doing. It's basically saturating here. It's not continuing the oscillations. So here The first part looks fine. So even though we have this shifted in between the integer samples, it still gives a good interpolation. And then here this extrapolation works fine for about half a period or quarter period. And then we get into the saturation. So that's kind of interesting. So that also means you always need to check. Yeah, so we see that we have a good interpolation for the X range of the training set, but the extrapolation beyond this training range is not really working. The resulting function from the network is the sum of the functions of the n nodes. And now we can try to see the basis functions, basically, those simple functions. To see the functions of the individual nodes, those basis functions, we can just keep their weights unchanged, set the other weights to 0. So basically now we tweak the weights of our network and plot the resulting function. For that we make a mask with zeros for the weights for layer 2, except for one node, and plot the function. Then we repeat this for every node in a for loop. So that's the trick here. So basically we set the weights of every node to 0 except for 1, so that the output is just the function from this one node. So here you can see it. Here's this for loop. Right. Here we create our mask. So here initialize it with a shape. So the shape basically takes the layer 2 weights shape. Here we initialize it with zeros, and then we take the node that is currently here in this for loop and set it to 1.0. Right, so that means after we multiply it element-wise, this one node will be unchanged. Yeah, and that's happening here. So here we have our model state dict. Here we access layer 2 weights. So again, this was the dictionary for layer 2 weights. And then we can write to those weights using the function data copy. Right? And data copy now takes as input the no weights. So that's kind of tricky, but it's actually good to know this trick, because then we can basically write our desired weights. So here we have the old weights and multiply with this mask, which sets everything to 0 except for this one node. Yeah, and then we can do the prediction. So here we have our X validation, so our validation set. Produce the output using just one node, and then we plot it. Right, and we do that for each node. So let's run this cell. Yeah, it does run. Right, so here again are weights. And here now the resulting basis functions. Yeah, so there should be 10, but only 3 of them are shown here as labels. So here you can see how they look like, and you can also see here in the end they all become flat, and that's why we have the saturation. But in between you can see we have different basis functions. So here, for instance, this looks like a shifted sigmoid function here. So this is responsible for this piece of the function. Here we have another shifted sigmoid function more towards the beginning. This is even more shifted, and so on. So you can see here, indeed, we have all shifted sigmoid functions, shifted in level in the y-axis, but also shifted here in the input in the x-axis. Right, remember we had 2 biases, one coming from the input and one going to the output. So that's the shift of the x and the y-axis. Yeah, so this shows that the resulting function is indeed a superposition of shifted sigmoid functions. Shifted and scaled, because they have different size here. Here you can see a big sigmoid function, and here's the small sigmoid function. Yeah, so that seems to work fine. So we can also try different architecture. So what we had so far is just one hidden layer, so a very shallow function approximator. And a different approach is this deep function approximator. Right? So instead of having a shallow or relatively flat network with only 3 layers, we can now distribute our nodes over more layers. So instead of going into the width, we go into depth, each containing fewer nodes. So the total number of nodes is maybe not so different. In this way, we obtain a more narrow and deeper network. In this example, we have 5 layers or four layers, but each layer has only 2 nodes, so that the total number of nodes is similar. So here you can see 2, 4, 6, 7, 8. So a total of 8 nodes here. It's actually slightly less than we had in our shallow network, but now more deep. So you can think of this being a different function approximation. So before we all had our shifted and scaled sigmoid functions, and now you can think of, in the end, we have our basis functions, but these basis functions consist of more complicated versions. So you can think of, here in the beginning we have the sigmoid functions, then the next complicated functions are compositions of sigmoid functions, and here these are compositions of sigmoid functions. So you can think of each layer being more and more abstract, containing more and more of components of our previous layers. So basically each following layer builds on the previous layer's components, and in the way the layers represent more complicated components. So here this is always similar to before. So now here we have 40 samples again in our signal, but 2 nodes of each layer, so much less. And here you can now see the network definition. Here we now have our 4 linear layers. Here they are arranged in this sequential function. So sequential takes a sequence of layers. So we start with the first linear layer, which has this one feature in, right, coming on the time axis. Out features is nodes. So here we have 2 nodes in this case, and we have bias. And then we have more hidden layers. So the next linear layer has nodes features in, nodes features out. Again, the next layer. And here we get the output layer, which has nodes in features and this one function layer, one output feature for our function. Again, we use the sigmoid as our activation function. And here we can see when we execute this, we connect the layers. So here layer 1, then we have the activation function after it, then layer 2, again activation function, layer 3, activation function, and then layer 4 without an activation function in this case. So we can let it run. So now we defined the object, and next we can instantiate the object again and create our signal again. So this is pretty much the same as we did before. We have our test set, we have our validation set. Here we instantiate our model again. Here we do the prediction before training. Look at the weights. It's interesting now to look at the weights because we have a different network. Again, define the mean squared error loss and our optimizer working on the parameters. So we can now run it. So the optimizer is not run yet. It's just we set up everything with the signals and the loss function and the optimizer. So here we can now also see the initial weights. So again, random values. And you can see here the weights. Here we have 2 values. Here we have 4 values because we have 2 input and 2 output. Same for the next one. And then we also have the bias. Here the bias is 2 values, then also 2 values, and so on. And yeah. And the last one has only 1 bias. So then we can actually let it run, do the optimization. So here I put the optimization in a separate cell, because then you can run it several times, because it turns out this is not so easy to optimize. So you can see we now have, instead of 10,000, I already went up to 20,000, so twice as many. And let's see how it's doing. So we can let it run. So we start at a relatively high loss function value here, similar to what we had before. But then the decrease is not as fast. You can see it decreases more slowly. 0.07, and several times we have this 0.07. So we can see, since we have this deeper model now, we have more complicated functions, and those more complicated functions are not so easy to optimize using gradient descent methods, because they have like narrow valleys and local minima. So that's the disadvantages of deep networks. The loss function becomes much more complicated, a much more complicated function of its weights, and the optimizer has a harder time finding a good solution. So here you can see we are at 0.06. So that's much larger than the 0.001 that we just had. So let's run it again. So now the model is not changed, so I can just rerun the cell, and the model will have the weights that we previously obtained as a starting point here. So let's try again. So now we have 0.06 here. And here you can see we have this 0.06, so we kept it. And now we can go down from there slightly. Yeah, so also in this case, maybe it's worthwhile to start from the beginning, see if we get a better starting point to obtain better solutions, because maybe it's now getting stuck in some local minimum here. Here the numbers all look pretty much the same, right? So this looks pretty much like a local minima, and remember we already had much better results in the previous case. So this might be a local minimum which doesn't give such a good result. So to start again, we would have to rerun the previous cell, because that's where we instantiate the model with random numbers. So now we have new random numbers. So now let's try this again. Yeah, starting point is not so good, but let's see. 0.07. 6.9. 6.7. Yeah, so it seems here now we are getting lower. So remember, we just got stuck at 0.688, I think. So yeah, maybe this is better. So let's try it again. Yeah, so here it's still decreasing, although not very fast. Yeah. So this to me looks like a case where we have to spend many more epochs to get to a good result, because you can see it still decreases, but very slowly. Right, so Here it would be worthwhile to have like a faster machine or using GPUs. And GPUs really can speed up the optimization here. And this is the reason why people need large GPUs, because when you have large and deep neural networks, training becomes very time consuming, and you want to have machines which are as fast as possible to finish within a realistic time. So having running times for large neural networks on the order of days can easily happen and is relatively normal. So this is just a toy example, and you can see even here in this toy example, it takes some time. Right? And now imagine instead of this toy example, you have a network which has millions of nodes, then this time here will correspondingly increase. Yeah, so it turns out that this ADAM optimizer which we are using now needs many more iterations than before. The resulting function approximation seems to be more smooth, and this is an advantage for generalization. Right? It has this smoothing property. Observe that the validation set now has a very similar loss as the training set. So let's see. Let's run this. So this was from a previous result. So let's see what it does now. Yeah, kind of similar. So here we can now see the training target. Again, our noisy function. And here the prediction output. And unfortunately, it is actually kind of modeling this little noise peak here. And it didn't get quite this first bump. Also the last one here. So it's actually not that great. Yeah, so the optimization had a harder time to fit the function despite the many more times used for the iterations. But often it is found that deep networks are better for generalization, which should give the loss function for the validation and test set similar values for training. So here's the validation set. Yeah, so here validation target, prediction output. So here the interpolation seems again to work fine. Then it didn't quite get the peaks here, and then also it totally fails with the extrapolation here. So it basically just goes into saturation right away. Yeah, so in this case it's maybe not that great. Yeah, here we have a loss on the validation set in our case of 0.063. And that's actually quite similar here to the loss on the training set of 0.065. So that's indeed the case, right? Validation and training in this case are very similar. That means we have good generalization. Yeah, we see that it does a reasonable interpolation with a smooth curve fitting. Yeah, sort of. So yeah, then we can also plot the resulting basis functions of it using the same trick as before. So resulting function from the network is the sum of the functions of the n nodes. To see the function of the individual nodes, we can just keep the weights unchanged, set the others to 0, and plot the resulting function. And for that, we again make this mask with zeros of the weights, except for one node. So here in this case, we use layer 2 and set the weights, the corresponding weights to 0, and then see what we get for the different nodes here. Yeah, and since we have only 2, this is the result. And you can see, yeah, maybe that's why we don't get such a good extrapolation, because both are saturating here. So that doesn't look too good. Yeah, okay. And that would be it for it. So I just encourage you to also do those experiments and try different optimizations and see what happens if you change things. Yeah, that's the advantage of these Colabs. Okay, then thank you for your attention, and then see you next time.